Hi, I'm Cooper, and this is Kepler's fourth law of planetary motion. Let's go.
You're probably thinking, momentum? I barely even know him. You do. You've known him since the beginning of the universe. The physical principle of the law of conservation of momentum.
What's up, guys? It's Cooper Wiseman. For the elastic collision, Zach's going to get pushed towards Nathan. Nathan will be at rest, and after contact, he's going to get launched by Zach's momentum.
Here's an explanation of that elastic collision. So we know that momentum, or P, is equal to mass times velocity, and my mass and velocity, both being greater than Nathan's, will send a large shift in momentum to Nathan since momentum is conserved in a system. Since my mass is greater, that momentum will be shown as velocity in the transfer.
For an explosion reaction, Zach and Nathan will initially be at rest with zero momentum, and the energy stored within muscles will be pushed against each other, forcing each other outwards, similar to an explosion.
In an inelastic collision, kinetic energy is not conserved like it is in an elastic collision. Instead, the most possible kinetic energy is lost in this type of collision. The results of this type of collision usually have the two objects stopping entirely or locking together and rolling off at the same speed.
If we want to examine the change in momentum of a non-isolated system, we have to take into account impulse, which is the forces acted on that system times the time interval. The initial momentum plus the impulse equals the final momentum.
Now moving on to our quantitative data, because we see this happens, but what's the math behind it? You already know we had to follow in the footsteps of our boys at Khan Academy.
In an elastic collision, kinetic energy is conserved, which means that the initial kinetic energy of the system is the same as the final kinetic energy of the system. For the elastic collision, we had two carts on a track, the blue cart and the red cart. I'll label the blue cart with mass 1 and an initial velocity 1, and the red cart with mass 2 and an initial velocity v2. V initial 2. We input these values, we weighed the two carts, and we inputted the initial values for both of these using a motion sensor in the first four columns of the data table. And then after the collision, we took the final velocity after they repelled with the magnets, v2 for the red cart and v1, and we recorded them in these two values, in these two columns. And using the equation P, or momentum, equals mass times velocity, we calculated the initial momentum for the blue cart based off the initial velocity and the mass, and the initial momentum of red based off the initial velocity and the mass. We then added these two values together to get the total initial momentum of the system. We did the same thing with the final velocities, this time multiplying the final velocities by the two masses to get the final momentum of the blue cart and the final momentum of the red cart. We added these two values together to get the total final momentum of the system. In a perfectly elastic collision, these two values, based on the law of conservation of momentum, should equal 0 or add up to be 0. However, we were not perfectly accurate, and we had an average error of 4.49%. In an inelastic collision, the most possible kinetic energy is lost during the collision. In this case, we had two objects stick together upon impact. We had two carts with a Velcro on either side, a blue cart and a red cart, set up as shown, the red cart with a mass of 1 and an initial velocity 1 being recorded by the motion sensor, and a blue cart initially at rest with no momentum or velocity up against a force sensor. As the red cart is pushed with its momentum, it comes into contact with the blue cart and they latch onto each other. However, there is still a small force applied to the blue cart from the kinetic energy of the red cart as it transfers the force sensor. This force in newtons is recorded in this column here. We then were able to calculate the integral, which is also known as the impulse, or average force multiplied by change in time, and that is not the change in time, or that's not the total time that it takes R to get from its initial point to contact with blue. That is only the time it takes or the time that the collision occurs within. So a very small amount of time. And on the lab quest, this is shown in a graph with the change in time or the total time on the x-axis and the average force on the y-axis, which means the slope of this would be impulse. And that is what we calculated using the integral in this column.
So as you saw in the video, we have the blue cart and we have the red cart, and they are launched apart by a spring. We know that the initial momentum, or P naught, will be equal to 0 since they're at a standstill, nothing's moving, nothing's going on, and that the energy will come from some store or some other thing like an impulse. In this case, it is the spring potential. And so to calculate what happened, what's going on, our error, we can use the mass times the velocity will give us our momentum. So for blue, we will do mass of the blue cart times velocity of the blue cart will equal the momentum of the blue cart. And this equates, as seen in our chart, we have the mass of B, the velocity of B, and then our momentum of B, which is 0.059. The same applies for the red cart. So we have the mass of the red cart, the velocity of the red cart will equal the momentum of the red cart, and that is equal to negative 0.056 rounded. And so in a perfect system, which this is not, these should cancel out. But with our error here, you can see that they didn't. That is likely due to friction or mismeasurements by the motion sensors. But it is still a display of conservation of momentum or net momentum. And that is all. Thank you.